Hello guys, today we are going to look at a topic in physics which is heat capacity. And firstly we need to understand the concept of heat. What does heat implies? Though generally we understand that heat is a form of energy, but not only that, there are more to do or more to talk about as far as it is concerned. When we talk about heat is regarded as energy in transit. Why? Because if a form of energy is meant to transfer, or let's say to be transferred or transmitted into another form, the energy must be converted or must be in form of heat before it moves. So that is why we call heat energy as a type of energy in transit. So that's the general definition, energy in transit. But there is a parameter of a body that determines the direction of heat flow. If heat is tend to flow from one body to another body, there is something that determines which body will lose the heat and which one will gain the heat. And that parameter is what we call temperature. So temperature difference between two bodies tells us the direction of heat flow. Though we said temperature is the degree of coldness or hotness of the body, accepted. Because if I say this body is 50 degrees Celsius, at least I'm measuring the property which is the temperature, and measuring it with respect to another and telling us, okay, the degree of coldness or the degree of hotness are different. But the simple and more technical, or let's say more advanced definition for temperature should be, it is the parameter or property of the body that determines the direction of heat flow. Because generally heat will flow from hotter body to colder body. Heat flows from hotter body to colder body. So heat doesn't flow from colder to hotter body. So when we talk about temperature, it is a property of the body that determines the direction of heat flow. So that is temperature. So but today we are going to look at heat capacity. Heat capacity, what does it mean? Anyway, heat capacity. This is defined as the quantity of heat, because heat is a measurable quantity. It is measured in joules. Anyway, you can denote it by whatever letter. I used to say in physics that whatever letter you wish to use in order to represent any variable is accepted. Why? Because sometimes we always say, okay, velocity is always v. No. If I decide to use r and say, let r be the velocity, then it is accepted. It is acceptable. So far, I have defined that, okay, my r is this. So it is acceptable. But now let's take heat capacity into consideration now. Heat capacity is the quantity of heat required to raise the temperature of the whole mass of a body by 1 Kelvin. You know, this mass, this body, have its mass. Let's give it a value, an imaginary value, because we have not measured that. So it's, let's say about 5 grams, or let's say, yes, 5 grams. Now, the quantity of heat that will be supplied to this body to raise the whole temperature of the body by 1 Kelvin is what we call heat capacity. The quantity of heat that I will need, not to melt it, and not to boil it, or not to make it hot. The temperature, the quantity of heat I will need to supply to it to raise the body, the whole body, by 1 Kelvin is what we regard to as heat capacity. So it is a quantity we can measure and we can give a value. So quantity of heat, which is heat capacity, or can be regarded to as quantity of heat required, is denoted by Q. Q means heat capacity, or quantity of heat, or quantity of heat. It is heat capacity or quantity of heat. That is what we call heat capacity. But the heat capacity of a body depends on some parameter. It depends on the mass of the body, firstly, and also it depends on the temperature difference of the body. What I mean is, if I am to study the quantity of heat required to raise the temperature of the body by 1 Kelvin, I am going to set up an experiment to know the initial temperature of the body, then supply a little amount of heat to it, and see the next temperature, I mean the change in temperature, So then the mass multiplied by the change in temperature is proportional to the quantity of heat required to raise the temperature of the body by 1 Kelvin, not the quantity of heat you supplied in the experiment. Anyway, I think let's get things right. The experiments involve supplying of heat to the body to get a temperature difference. So once the temperature difference has been established, it will be multiplied by the mass of that body. Then the product of the two is directly proportional to the heat capacity of that body, not the heat I supplied to the body to get the temperature difference. So now we can say the quantity of heat Q is proportional to the mass times the change in temperature of the body. So don't forget where M is the mass of the body and change in temperature, change in theta represents change in temperature of the body. So if I have this, anytime I have proportionality, I'm meant to introduce a constant. So what constants am I going to introduce? I can use any letter to represent my constant anyway. So but here I'm using letter C. So I have Q is equals to MC change in theta. So we have a formula here. C is the constant, while mass times change in temperature is what we have here. Now this C is a constant called specific heat capacity. Specific heat capacity. Anyway, quantity of heat Q is measured in the quantity of heat Q of the body is measured in joules per Kelvin, since it is the quantity of heat required by the body for the temperature to be raised by 1 Kelvin. So the quantity of heat required to change the temperature, to raise the temperature by 1 Kelvin, so it is measured in joules per Kelvin. The mass is measured in kilogram, kg. Then we have change in temperature measured in Kelvin. So C is the constant we derive from that little expression I just made there. And this C is called specific heat capacity. It is regard to our specific heat capacity. Let's give a definition for heat. Specific heat capacity now talks about, initially I made mention that the temperature required, the quantity of heat required to raise the temperature of the whole body by 1 Kelvin is heat capacity. Now let us consider that I divide the mass of this body into units, to the smallest unit, or as small as 1 gram. So what quantity of heat will be required to raise a unit mass, a unit out of the whole mass, a unit by 1 Kelvin? The quantity of heat that will be required to raise a unit by 1 Kelvin, a unit mass. We are talking about kilogram, because most of what we are going to be doing here, we are going to be making use of our SI units. So the quantity of heat required to raise a unit mass of the body by 1 Kelvin is regard to our specific heat capacity, and it is denoted by C here. So let us derive a unit for this as a constant. So from here, from this expression, I have Q equals MC change in theta. So from there, I can make C the subject of formula, then that's divide both sides by M change in theta, M change in theta. So with that, this goes with this, then C will be equals to Q all over M change in theta. So from here I can get the unit. That is how sweet physics is, because once you know the formula for a particular quantity, you would be able to deduce the formula as far as derived quantity is concerned. So now, quantity of heat is measured in joules. As I have said earlier, mass is measured in kilogram, and change in temperature is measured in Kelvin or Celsius. So, but let's use Kelvin as an SI unit. So the unit for specific heat capacity is now going to be joules per kilogram per Kelvin, or rather written as joules per kilogram per Kelvin. Joules per kilogram per Kelvin. Now, the specific capacity I said is a constant, and is a constant for all forms of substance like water. The specific heat capacity for water is constant. We have that for aluminium, we have that for various materials, but for that of water it is 4200 joules per kilogram per Kelvin. So this is specific heat capacity for water. So I'm putting a subscript W here to indicate that the specific heat capacity is for water. So now let's proceed to another aspect. We need to talk about, we need to make use of this formula in solving question. Thereafter, we go to how to determine the specific heat capacity of the body and the method we are going to use. So let's try some question. Okay, let's try simpler ones. Firstly, the question says, what is the quantity of heat? What is the quantity of heat? So from that question, I like catching it young. Catching my question young from the beginning, I pick out my parameters. What is the quantity of heat? So from that question, it shows we are looking for quantity of heat. It indicates we are looking for quantity of heat. What is the quantity of heat that will be given out if a bar of mass, if a bar of brass of mass 350 grams, so the mass involved is 350 grams, is cooled from 95 degrees Celsius to 20 degrees Celsius. Is cooled from 95 degrees Celsius, that is the initial temperature, is 95 degrees Celsius to 20 degrees Celsius. That's the final temperature is 20 degrees Celsius. So from here we can see that heat is not supplied to that body. Heat is removed from the body. It is being extracted from the body in the process of cooling anyway. So now we are meant to find the quantity of heat, and we were given the specific heat capacity of brass, which is specific heat capacity of brass is given to us as 380 joules per kilogram per Kelvin. So with this, it is very straightforward using that formula. I can easily calculate. The change in theta I wrote here means change in temperature. It means change in temperature. So, and the change in temperature, it means the final temperature minus the initial temperature. So we have the quantity of heat will be equals to the mass, which is 350. But anyway, we need to convert the mass to kilogram. And to convert the mass to kilogram, we have to divide by 1000. So that's 350 divided by 1000. So that gives 1, 2. So the mass is going to be 0.35 kg. 0.35 kg. So to calculate this now, quantity of heat will be equals to the mass 0.35 times the specific heat capacity, which is 380, times the change in temperature, that's 20 minus 95. Yes, we have to subtract the final minus the initial. This is the final, this is the initial. So subtracting the final from the initial is going to be negative because it is being what? Extracted. It is being lost by the body. So it will definitely be what? Be negative. So let us calculate that. We have 0.35 times 380 so that gives us 133 multiplied by 20 minus 95, that will give us minus 75. So from there we have 133 times 75, which is quantity of heat equals minus 9,975 joules. So this is the quantity of heat that is being extracted from such body to get the temperature difference. So that is a typical example of how question is being solved. a straightforward question anyway. So let us go straight to how to determine the specific heat capacity of the body. Determination of specific heat capacity. I'm going to short it this way, of the body. Good. Now, how do we determine the specific heat capacity of this body, of any body? It is very simple. We have to get 2 or 3 bodies involved anyway. Anyway, the first one must, the 2 bodies. Out of the 2 bodies, we must have one of which the specific heat capacity is being known and the other is demanded for. So from there, we mix them together in a series of process. Then we calculate or we work out the specific heat capacity of the unknown. How do we achieve this? How do we achieve that? How do we determine the specific heat capacity of the body? As I have said, it is very easy because there is a law called law of calorimetry that says when 2 bodies are in contact, one loses heat while the other gains heat as a result of temperature difference. Anyway, as I've said earlier, heat moves from colder to hotter body. So one loses heat and the other one gains the heat. So the law now states that heat gain by a certain body is equal to the amount of heat loss by the other body. So meaning that if I am gaining heat, the amount of heat I gain is equivalent to the amount of heat loss from the source that supplied heat to me. Various methods that can be used to determine specific heat capacity. We have liquid by mixture. That involves probably water and alcohol. Liquid by mixture. We have liquid to solid, or we call it solid to liquid. Solid to liquid method, that is in case of brass and water, we are meant to determine either that of the solid or the liquid. And here, liquid by mixture, 2 liquids, we are meant to determine either of the one of the 2 liquids. Then we have liquid to electrical or electrical to liquid. So electrical method can also be used to determine the specific heat capacity, since the amount of energy dissipated by an electrical sector can be calculated using various formula, just like PT, IVT, and so on. Then we can equate it with the quantity of heat received by the body. We are meant to determine the specific heat capacity. We are going to have a formula like PT equals MC change in theta. The quantity of heat gained by the body equivalent to the quantity of heat lost by the electrical process. Then we have other formulas that might involve depending on the parameters we're given. We have I square R T. These are what electrical energies, so which we can equate to get the specific heat capacity of liquid. Anyway, so let's look at questions that we generally explain what we're talking about in these various methods. Let's check up questions. Okay, the first question we have here is electrical to liquid. So a 500 watts heater. So that means the power of the heater is being given to us, 500 watts heater. So this question quickly talks about electrical to liquid. Anyway, a 500 watts heater, so that the power equals 500 watts heater. 500 watts heater is used to heat 0.6 kg of water. So the water of mass 0.6 kg is being heated from the initial temperature, which is 25 degrees Celsius, is heated to a temperature of 100 degrees Celsius. So this is the first temperature, this is second temperature, this is 100 degrees Celsius. So from there, in t seconds, that means anyway we have a time difference in t seconds. So t1, that's it takes in t seconds, t1. So then if another heater is used to heat 0.2 kg of water, meaning we have two heaters involved here, and another heater of power 1000 watts is used to heat 0.2 kg of water. So we have water of mass 0.2 kg. So this is the first second body of water. So now from 10 degrees Celsius to 100 degrees Celsius, from 10 degrees Celsius, so that's the initial temperature for that is 10 degrees Celsius, to what? Second temperature, we have 100 degrees Celsius. Anyway, I can see that the only thing that is different is the masses and the initial temperature of water. One is colder than the other, so it's the time ratio. We are meant to find anyway find T1 over T2. T1 over T2. We are meant to find T1 over T2. So this is what the question demands from us. T equals MC change in theta. So for the first set of water and power, we're going to have T equals MC change in theta all over P. That's T1. Yes. So this is the first one, the first formula to solve the first set of experiments. Let's call it experiment. Then we have T2, which is also equals to, this is power 1, and this is power 1, this is power 2. So we have, and this is mass 1. So T2 is going to give us M2C change in theta all over P2. So with this, we can easily solve out and get the time, and we will be able to find the ratio of the time. So from the first phase of question, T1 will be equals to M, which is 0.6, times C, which is, anyway, the constant is 4,200, but let's see the constant given to us. We can do that in terms of C because in the question we were not given the specific heat capacity, but neglecting the fact that we know heat, that doesn't mean we can just put it. But since it is not given to us in the question, we work it out in terms of C. So we have times C multiplied by change in temperature, so that's going to be 100 minus 25 all over the power, which is 500. So T1 is going to give us 0.6 C times 75 all over 500. So let's work it out and see what we're going to get. 0.6 times 75. So that gives us 45. So we have 45 C all over 500. So T1 is going to give us 45 all over 500. So that's 0.09. So T1 is 0.09 C. Don't forget the unit of time is seconds. So we have this. So the next one says we should determine the second temperature, then from there we find their ratio. So how do we determine the second temperature? We have T2, which is equals to MC change in theta over P2. Don't forget this M2. So here we're going to have 0.2 times C into brackets 100 minus 10 all over 1000. So from there I'm going to have 0.2 C into bracket 90 all over 1000. So I'm going to have 0.2 times 90. So that gives me 18. 18C over 1000. So 18 over 1000 gives me C2 equals 0.018 C. That will be in seconds. So for us to calculate T1 over T2 as required by the question, so then we say T1 all over T2 is going to give us 0.09 C all over 0.018 C. So C goes with C. 0.09 divided by 0.018. So there we have T1 over T2, which is 5. So we have 5. Anyway, it's not going to have a unit because seconds will cancel seconds. I will not have anything else. So that is one phase of question that involves that. So we have series of questions that might involve mixing of two mixtures or derivatives. Let's go for another one. So now let's check another one. Our most asking questions. Okay, let's check this. Sometimes I didn't mention this method, but we can actually solve the question on it. A waterfall is 1260 meters. So we're talking about a waterfall here. A waterfall of height 1260 meters. That's waterfall, that's height. The height of the waterfall is 1260 meters high. Calculate the change in temperature of the quantity of water that falls from the top to the bottom of the waterfall. Given that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin, and we are also given acceleration due to gravity. So we are given only this as this, acceleration due to gravity as this, and we are also given the specific heat capacity for water to be 4,200 joules per kilogram per Kelvin. And we're talking about a waterfall here. So talking about a waterfall, that is, we're looking at a distance, a place where water is of. We might be familiar with that in some places where water, there is a downpour of water from a particular height of rocks and so on. So the waterfall in bringing, there is energy in that as well, and there is energy in form of heat loss as a result of that process of downpour of water. So this energy is given by mgh. We can relate it to the quantity of heat gained by the water, which is what? MC change in theta. But we're talking about a single water, so what will happen? The mass will be the same. So we have this. The mass will be the same. So we have this. So GH will be equals to C change in theta. So we're definitely looking for, we're actually finding the change in temperature. So we are looking for the whole this. We're looking for the whole this. So we have change in temperature is going to be GH over C. So that's going to give us 10 times 1260 all over 4,200. So that will be 1, 2. This goes with this, and this goes with this. So we have 126 all over 42. So by the time we calculate that, we have the change in temperature to be so we have 126 divided by 42. So that gives us 3. The change in temperature is just 3 degrees Celsius. So as far as that question is concerned, we have the first solution to that. So let's check another series of questions that might come. When two objects P and Q are supplied with the same quantity of heat, so I think we can catch a question young from here. So let's pick it. We are talking about two bodies P and another body Q. They are supplied with the same quantity of heat. The temperature in P is observed, the change in temperature in P is observed to be twice that in Q. The change in temperature in P is discovered to be what? Twice as that in Q. So if the masses of P and Q are the same, they have equal masses, they are supplied with the same quantity, with equal quantity of heat. So calculate the ratio of the specific heat capacity of P to Q. So it is very easy. P ratio Q, talking about their masses, is the same. Is 1. Let's say it's 1. The ratio is 1. The ratio of mass P to Q is 1. Good. And we are also talking about their specific heat capacity. Their specific heat capacity from the formula MQ equals MC change in theta. So specific heat capacity is going to be what? Q all over M change in theta. So the ratio of the specific heat capacity of P to that of Q is what we are meant to calculate. So we are looking for CP ratio CQ. Good. But there is one fact I will need to establish as far as the question is also concerned. We have the change in temperature in P. That's change in temperature in P, as it is said in the question, is to be twice of that in Q. That means we have 2 change in temperature of P is equals to change in temperature of Q. Meaning that the change in temperature of Q is twice that of P according to the statement, because in the statement it is written as, it is observed that change in temperature in P is observed to be twice that in Q. To be twice that in Q. So from there we can establish the fact Cp is going to give us, according to this formula, Cp will be Q all over 2m change in theta. Why? Because the change in temperature in P is 2 times that of Q. If we relate it to the ratio of CQ, we are going to have Q all over M change in theta. Don't forget that they have equal mass and the same quantity of heat flows through them. So from there we can easily cancel out the masses and cancel out the quantity of heat. So let's solve it out from here. I can easily cross multiply. So the quantity of heat are the same. I have Q M change in theta is equals to Q 2m change in theta for P. Anyway, this is for small q. So this goes with this, and at the same time, this will go with this. So we have change in theta for q is equals to 2 change in theta for P. So the ratio of both, anyway, we are meant to find the ratio of specific heat capacity of P to Q. P to Q, so that means P comes first, then Q follows. So we are dividing both sides by Q. So here we are dividing both sides by change in temperature of Q. So we are going to have change in theta Q equals to change in theta P. So having such, we can divide both sides by change in Q and change in Q. Change in theta of Q and change in theta of Q. So this gives 1 equals 2 change in P, change in theta P all over change in theta Q. So everything here is going to give us, dividing both sides by 2 again, so change in theta of P all over change in theta of Q is equals to 2 to 1. So the ratio is going to be what? 2:1. So the ratio of their specific heat capacity Cp to that of Cq is equal to 2:1. So we have easily determined that. Very, very easy. So that is another form of question. So we can also search for more question that involves mixture and determination of specific heat capacity. And mind you, when we're given formulas like that, it is not compulsory we are meant to determine specific heat capacity alone. Just like that of the waterfall I just solved, we determine the change in temperature while we are given the specific heat capacity. So series of questions can come that way, and we are meant to find any other parameter other than specific heat capacity. So let's look at one more question as last question on this topic. I want that to be a kind of question that has to do with liquid by mixture or solid to liquid. Now, let's look at this question. A metal of mass mass of metal, just to differentiate the masses. So a metal of mass 0.5 kg, 0.5 kg is heated to 100 degrees Celsius. We don't know the initial temperature, but we know it is heated to what? 100 degrees Celsius. So that is change in temperature for the metal is 100 degrees Celsius. And then transferred to a well-lagged calorimeter of heat capacity. I mean, the calorimeter is well lagged. When we talk about lagging, we are talking about using an insulator to cover or placing a conductor into an insulator that will prevent heat loss. Lagging has to do with prevention of heat loss from a container. So the calorimeter is well lagged, and the heat capacity of the calorimeter, talking about heat capacity, that's Q equals 80 joules per Kelvin. 80 joules per Kelvin. Containing water of heat capacity. We're talking about water now. The calorimeter contains, there's quantity of heat in the calorimeter, C. So the calorimeter contains water, and the water is of heat capacity 420 kilojoules, 420 of its capacity, 420 joules per kilogram. That's its capacity of water is 420 joules per Kelvin. 420 joules per Kelvin at 15 degrees Celsius, meaning the calorimeter and the water maintains the temperature of 15. That's temperature equals 15 degrees Celsius, because once the water is 15 degrees Celsius and there is no heat loss or gain between the water and the calorimeter, then the temperature of both is 15. So from there, if the final steady temperature of the mixture is 25, so after mixing the metal with water in the calorimeter, that means we have three materials involved. The calorimeter will gain heat from the water as the metal loses heat to water. So now the temperature of the mixture altogether is 25 degrees Celsius. So we have third temperature, unless the second is 25, or temperature of mixture is 25 degrees Celsius. Find the specific heat capacity of the metal. So we are meant to find the specific heat capacity for the metal. It's very easy. Heat gain is equal to heat loss according to law of calorimetry. So now, which one is losing heat or which one is gaining heat? The calorimeter and the water is gaining heat. So the side that is losing heat loss is M, that is the mass of the metal, multiplied by the specific heat capacity of the metal which we are looking for. Then the change in temperature, anyway, the initial temperature of the metal is 100, so by the time it is mixed, the new temperature of the three of them becomes 25. So it has lost about 25 degrees Celsius of heat. So we have multiplied by change in temperature. Anyway, this is not the change in temperature, this is the first temperature of metal is equivalent to that of calorimeter, mass of calorimeter. We're given the heat capacity of the calorimeter. So meaning the calorimeter Q equals MC change in theta. So we have Q here. That is, we have the mass of the calorimeter. The heat capacity of the calorimeter is given. So we have Q calorimeter plus Q of water. And don't forget there is a change in temperature, so which we need to relate with them all. So the initial temperature of water and calorimeter is 15. So we can multiply it by that change in temperature. So here we have the mass, which is 0.5 multiplied by Cm we're looking for. Then times, we're going to have 25 minus 100. All equals, we have 80 plus 420 multiplied by 100 minus 15. Or let's say no, the initial temperature is 15, while the final is 25, not 100. So we have 25 minus 15. So that gives us 0.5 times Cm times what? Minus 75 is equal to, by the time we had this, we're going to have 80 plus 420, that is 500, multiplied by 25 minus 15, that is 10. So we're going to have 0.5 Cm. Anyway, we can maintain negative, positive sign here, because it's losing heat anyway. It shows it's losing heat at this moment. So we have 0.5 times 75. So that's going to give us 36 points or 37.25. So we have 37.5. So 37.5 cm is equal to 5,000. So from there, the specific heat capacity is going to give us 5,000 divided by 37.5. Anyway, we can still use the negative sign. So 5,000 divided by 37.5. So that gives us minus 133. 133.33 joules per kilogram per Kelvin. So these are forms of questions that you might meet when you talk about heat capacity and specific heat capacity. Thanks for watching. Please subscribe to our YouTube channel. It is free. Thank you.